My name is Mahdavi. I'm the head of the Department of Building Physics and Building Ecology at TU Vienna. I present this work also on behalf of my colleague, Ms. Helene Teufel, who works with me on a number of related projects about radiant cooling. As you're all aware, and I don't need to expand on this very much, due to multiple factors such as the climate change and urban heat island effects, the requirements in built environment for cooling energy has rapidly increased, and it seems that the conventional methods to provide that service is deemed not to be efficient and sufficiently sustainable. Radiant cooling, specifically something that we refer to as occupant-centric radiant cooling, may have the potential to mitigate that situation, to provide cooling services in a more energy efficient and sustainable manner. So the idea that we're pursuing is to take the conventional radiant panels and bring them closer to the occupants, and also consider if it's possible to combine such elements with technical features that let them accommodate surface condensation. Again, as you all know, surface condensation is a challenge for radiant cooling because the surface temperatures of radiant panels cannot typically go below the value of the dew point temperature, prevailing dew point temperature, in order to avoid condensation. This is especially critical in case of ceilings or ceiling-mounted radiant panels. So if you're able to accommodate that, we can go further down with the surface temperature, increase, so to speak, the effectiveness of radiant panels. We can maybe even combine those panels with vegetation elements and make them into a attractive feature of the indoor environment. So to pursue this, we looked at these issues, condensation risk, humidity control, and considered a case study, a computational case study, basically inspired by the configuration of our own offices here at TU Vienna, and see what would be the potential, what can we achieve in terms of provision of comfort with such elements. So we took a typical workstation in our office area, and we assumed on the summer conditions, the warmest months of the year, we would install maybe 1 or 2 radiant panels in these workstations and look at the, in this case, a classical indicator of thermal comfort, which is the predicted mean vote or the predicted percentage of dissatisfied, and use computational methods in order to address that potential. So we look at the indoor conditions. We have measured values indoor environment in case of temperature and relative humidity and mean radiant temperature. And we could play around different scenarios where, for instance, we avoid condensation, we keep the panel surface temperatures above the dew point, and we also try to avoid radiant asymmetry. That means that we should avoid that the surface temperature of the panels have not a much too large difference from the overall ambient, because that is assumed to cause local discomfort in terms of radiant asymmetry. So we look at different scenarios. We said, what if we just have 1 panel installed at the close proximity of the occupant, or maybe 2 panels? And what, in case needed, we could also augment the system by an auxiliary ventilator, desktop, so to speak, ventilator, which increase the airflow and hence would also contribute to provision of thermal comfort. These are some of the results of the simulation. You see in this case as an example, again from the year 2017, with 1 radiant panel, you see the course of the air temperature, which can be pretty high, up to 30 degrees Celsius and more. These are indoor temperature measured values. You can see the dew point temperature. In this case, the control scenario was to avoid, as I mentioned before, for the surface temperature to go below the dew point temperature. And these are the resulting PMV values. They can be partially quite high, go beyond 1. And to provide a more general overview of the results, you see here graphs that show basically the percentage of time during the working hours in these offices where the PMV value was above a certain threshold, for example, 0.5, or if you have less stringent requirements, more than 1. And as you can see, without any measures, a fairly significant percentage of the time, the PMV is above 0.5, more than 40%. Even with the more relaxed requirements, is almost 15% beyond 1. By installing one radiant panel, we can reduce this time significantly down to 23%. By 2 radiant panels, further down to 12%. And by addition of a desktop ventilator, it could be pretty much reduced to an acceptable level. Of course, these results are relevant for the climate of Vienna, conditions in Vienna. In other conditions, the results would have to be recomputed, but it seems that if we are capable to meet the requirements that we discussed, bring the radiant panels closer to the occupants, avoid for surface condensation, and technically deal with that, we would be able to effectively make use of the radiant cooling technologies in terms of a more energy efficient, more sustainable, and if designed well, maybe even more attractive solution. We have pretty much discussed already the conclusions about future research or ongoing research. We are currently in the process of installing prototypical instances of these user-centric radiant panels and test them empirically such that we have a confidence that these can be introduced into the architectural spaces and provide the type of performance that we expect. Thank you for your attention.